Welcome to the presentation of our paper PIMOD, a tool for configuring single-board computer operating system images. This work is joint work by me, Jonas Höchst, by Alva Penning, Patrick Lampe, and Bernd Freisleben. So, how does your research project prototype new ideas? We think that most people use more or less generic devices, such as the Raspberry Pi or devices of other vendors like RockPi or Libre Computer, or even NVIDIA, which offers some GPU acceleration, and prototype their ideas by using custom software there. And the great thing about those devices is that they are easily to obtain and easy to set up. You don't need to install your operating system, you just grab an image from somewhere, flash it to the SD card, and run the device. And you can start to use it and start to develop your ideas. So this is the classical way of setting up such a computer. You download the OS, flash it to an SD card, access the device somehow, made via keyboard or SSH through the network or via a serial console, and then you install and configure your software you want to use. And you basically do this for each and every device you want to use in your study or in your research project. This is nice because it is very easy to do, and you can even do some scripting and elaborate on this process and make it a little faster. But it has some disadvantages. Mainly, you have to do it for each and every device. Then, a second alternative, and I'm sure you've done this before, is to do this exact process, but then after you set up your initial device, you retrieve from the one SD card you have a golden master image. And this is then on your workstation, and you can replicate it to more SD cards. You can even shrink the image to optimize for flash speeds, and mainly you have to remove some host-dependent configuration, such as the host name that was configured or SSH keys that were set up initially. But the initial installation remains mostly manual, so you do this boot up process in the which was done before on all the devices on one device, and then retrieve the image. Then there's another alternative. This mainly is a little bit based on the distribution you use. Some offer configuration script to be run at the first boot. And then what you do is you flash the image, then add your custom configurations such as Wi-Fi credentials or some passwords or even some software to be installed. And then if you boot the device up at the first time, it will self-configure itself and will install software and so on. Problem is, it's still done on all the devices, meaning they all need to access the internet, and there's some kind of overhead in these terms. And what is if there's an exception? What is if some server is not reachable? You have to look after them and have to check whether everything got installed right. And we think we can do a little better. Coming to PIMOD, which is the center of our work here. We try to enhance operating system images, the ones we've used before, like Raspbian, using virtualization. And the idea is to have one central configuration file called a PI file, which is loaded and interpreted by our software and then executed in the respective order. So, for example, it retrieves an operating system, may it be defined by a URL or even in the local file system, then executes parts in this operating system via virtualization. So you can install some software and configure the software just like you would on the real device, but it's running on, a virtual host. And this then leads to the golden master. And the nice thing is, you don't have to swap out any SD cards. There's no manual process. And you do it install once. You create the image, the golden master once, and then replicate it to all the SD cards you want to provision. And this leads us to our example we want to show you. Here you see on the right a simple listing of a PIMOD file, which does nothing else but downloading the operating system, increasing the image size by 100 megabytes. You see it in line 5. then run a configuration script, which is part of the distribution, to enable the serial console. Then we do an update of the packages and upgrade them to the latest software versions. And in the end, install a local SSH key so that we can later on log into the machine. The commands on the left side, from, to, pump, run, these are commands that are interpreted by our PIMOD software. And the rights are the parameters for those. And as you see for the run commands, that are just commands that are run inside the container. Our instruction set is rather limited. You see 8 commands on the left which are used in our language. And to be fair, this language is highly inspired by Docker, which I'm sure most of you know by the time, which is nice to have your software on a local machine contained inside one nice little container. And the same thing we think is useful for those single board computer images and systems. So what are the design goals of our system? First of all, we want fast execution. We don't want to boot the whole operating system because in all the distributions, there are so many variations of hardware checking, and all these different boards have such a high variety of hardware that we cannot disable or emulate all the different boards. So no full system emulation, but instead only running the dedicated applications that are there. And for this, we use the QEMU-based system emulation. So you can just run the ELF binaries which are in the system on your host system of a different architecture. We want support for continuous integration. Most people use it nowadays to just check whether their commits work, whether they did some errors, and check if their software compiles. And we want to have this on the operating system level as well. We want to do automatic builds. Also, we want to have some kind of host system support. There are some programming languages which enable nice native cross-compilers, and we want to use this power we have. We will come to this back later. Our implementation, we base PIMOD basically on 3 stages. The first being the setup. That cares about where does the image come from, where does it go to. The second is preparation. In this stage, we care about increasing the image or shrinking the image. And the third stage is the change root stage, where we actually mount the image and then can execute stuff inside the image. To evaluate PIMOD, we first off check whether we reached our design goals. So remember, we want to have usability. We want to have an advantage compared to regular configuration schemes, such as flashing the stuff. And we want to utilize more powerful hardware. We have build servers back there, which are really powerful, and we want to use them. Also, we want to have some kind of modern software development, and all 3 of those goals are met, as we think. Generally speaking, we want support for various Linux distributions, and we checked multiple, and they worked fine. So in this case, Raspbian, Ubuntu, OpenWRT, which is a router distribution, CentOS, Fedora, Kali, OpenSUSE, and so on. Also, we wanted support not only for the Raspberry Pi, even though it's called PIMOD, we wanted support multiple single board computer systems, and we tested for Libre computer boards for the Raspberry Pi models, even the NVIDIA AI development board, which has GPU acceleration is supported, and the Odroid boards, and so on. So really, we did make a general point here, not only for the Raspberry Pi. In terms of costs and benefits, virtualization, of course, is an overhead, but we evaluated that, and I want to present that now. So we compared a Raspberry Pi 3 Model B against a mid-class build server. One has to say, of course, the RAM is a huge difference, and probably the network and the storage is also a big difference in terms of speed. And everything we did network-wise and I/O-bound was really faster on the build server, of course, because we have a fast server network connection. Remember, the Raspberry Pi is limited to 100 megabits. Also, the build server has a fast NVMe drive, resulting in insane write and read speeds, which we just cannot have on a Raspberry Pi with an SD card. But in non-native computations such as cryptography, hashing and signing, we were a little bit slower. But as you may see from the figure on the right, the times are comparable. So the third, for example, is HTTP, where really there is a huge difference, PIMOD on the build server compared to the Raspberry Pi native. But if you compare it then to HTTPS, you see the build server is even a little slower because all the libraries doing the crypto-intensive stuff and so on are running virtualized and are running slower. But this is a trade-off which is rather okay for the sake of integration, continuous integration, and the non-manual execution of our Pi files. Yeah, to validate extensibility, we have an example here. You see in the first line, we get the image from an HTTP resource, so it gets downloaded, gets gzip decompressed, and then used by PIMOD. The to parameter is set by an environment variable. In this example, we use the variable device, which may be a hint that you can use PIMOD to flash directly to an SD card. So you don't have to create the image on your hard drive, but can directly work on the SD card if you want to. Then, line 7, we source another Pi file. So this is possible so that you can modularize some kinds of configuration which you have over and over in different configurations and just include them into your main Pi file or Pi files, so to speak. Then we have Unix pipes and here documents, which you see in line 10 and 13. In line 10, in the case, we want to include the local SSH key as authorized host, so you can directly SSH into the machine. Here documents are nice to have, to not have a configuration file, but just to append to another configuration file that's already on the machine. And finally, in line 21, you see the Go cross-compiler compiling a delay tolerant software suite, which is just a lot faster if you do it on the host. And we showed here that you can do it on the host and then just install the binary, which is compiled on the host machine to the operating system, which is created by PIMOD. Yeah, why do we actually use PIMOD? So I am part of the Nature for Zero project, which is all about sensing biodiversity, and we have those sensor boxes you see in the upper left, which are really hacked together and just a prototype. But what we do there is we have all the resources to create this image, which runs in the field in the cloud. And I, as a computer science guy, create some configuration for that, install some software and fix bugs and so on. And then in the end of the day, I push my changes to GitHub and create a tag. And whenever a tag is created, GitHub Actions is used to build an image, which then can be used by the guys in the field, download it, flash it to the units, and then use it. So all the integration into the project is going a lot better through this process, and not to hand over images by a USB stick or something like that. It's just a more modern way of integrating software development and field work. What we want to do and what we think we can improve. We want to some kind of look into reducible builds. At this moment, builds are reducible in some way. They install the same software, they have the same configuration files, but they are not bit identical. This is mainly due to timestamps, because, well, the images are created on different times, and this differs then. Also, the software itself may not be reproducibly built on their build servers or on our machine, because there are slight variations. We also want to look into caching. Only the changed parts of a Pi file need to be executed. So if you have like 60 lines and then change line 61, only that last line needs to be executed again. This could maybe be implemented using snapshots file systems or something like this. and we think we can make more improvements here. And of course, we want to see this tested and you evaluate it in the wild and in other use cases. It matches really well for our sensor box use case, and I think it does for some other use cases as well. So if you're interested, give it a try, download it. There's also a Docker container which you can run it in if you don't want to mess up with your system, or if you have, like me, a MacBook which does not run Linux natively. You can just run it via Docker and create your images there. Have a good time. Thank you. And if there are questions, I heard the GHTC stream is live now, and you can just ask them, or later on via mail. My mail address is written down there. Thank you very much.